I recently checked out Optimum's tech video, which he deleted his 9900k and applied liquid metal for direct die cooling. He achieved a 13-degree drop at average temperature, and this is very interesting to me. But I have never seen anyone trying using normal thermal paste for direct die, and that's why I want to conduct my own experiment. For those who are interested in doing this, I really recommend the Rockit Cool because they have almost every tool that are needed for deleting a CPU, from mainstream to high-end. For $50 with no tax and free shipping, I could get a full package for deleting, removing soldering from the 9900k, and a frame for direct die cooling. This is much better value from the kit from Debauer, and you can also get multiple tutorials from Rockit on their YouTube channel. Within 5 days after ordering, the package arrived at my house. This carry box is used to keep the tools and looks pretty nice. Next is the direct die frame. A Wiha screwdriver for removing the motherboard CPU retention bracket. They also includes extra screws for mounting the direct die frame, unlike the Debauer kit, which requires reusing motherboard screws. Then there's a bag of Allen wrenches and screws, which I use for deleting. Next is the deleting kit, which is pretty heavy. And finally, a bag contains some quicksilver and flesh polish for removing soldering and cleaning up the CPU. The motherboard that I'm using is Asus Strix Z390i. The maximum clock speed that I have achieved is 4.9 GHz, and I hoped by doing this, I could reach 5 GHz without crashing the system like before. Before doing anything, first I remove the standoff of my AIO from the motherboard. Rockit Cool includes a pack of washers for both air coolers and AIO water coolers. These are used for lowering the height and helping the cooler to touch directly on the die. To install, simply place tubes for each corner of the AIO backplate. Next, I use tape for keeping the CPU backplate from dropping, because later I will remove the 3 screws that was holding it. Next is unscrewing the retention bracket. I highly recommend keeping the CPU in the socket to avoid dropping a screw on it and bend pins. I saw one guy on YouTube that dropped a screw on the socket of his brand new Z390 motherboard. He was lucky that he did not bend any pin, so safety first. Wow, this is the first time I've ever held a CPU without a heat spreader IRL. Next, I use a piece of plastic to scrape off the adhesive residue. After cleaning the CPU, the next step is using Quicksilver for removing the soldering. I use tape to cover everything except the die. This is used to avoid shorting the contact area on the CPU surface, which can definitely kill your CPU. After spreading it on the die, I just left there for more than an hour so that the Quicksilver can dissolve all the indium. I sometimes mix it up so that the Quicksilver can get into the lower layers. If it feels rough when touching with the tip, then there's definitely still soldering on the surface of the die. Because the indium solder is much softer now, I could use the Q-tip to scrape on the surface of the die to clean it. I added one more drop of Quicksilver to accelerate the process. When the solder is no longer sticking on the surface of the die, using alcohol is the best way to clean off the liquid metal. After that, fleece polish is used to make the die shine. When it looks like a mirror, things pretty much complete. I used alcohol to clean off all the residue and the CPU was ready to go. After carefully drop the CPU in the socket, I added a little bit of thermal paste on the contact points so that if I plan to use liquid metal and the liquid spilled out, I don't short those pins. Next is installing the frame, and I think this is the step that you know how. At this point, everything are ready to go. For this experiment, I used the Nocturne thermal paste as it is the best paste I have in hand. If it works, changing the CPU cooler could not be easier. Well, it failed completely as the temperature jumped to 98 degrees in less than 3 seconds after clicking the run button. I had to stop the test because I didn't want to cause any damage. I was worried that my CPU block did not make enough contact with the die, so I removed to check it out. The thermal paste was well spreaded, and everything seems normal. I cleaned it up, repasted, but the temperature was still over the top. I am not the expert to explain, so here are just my guess. It performs worse because of the heat transfer rate. Even though we have lower Z height by doing direct die cooling, in the first case, the indium solder obviously have higher thermal conductivity than the normal thermal paste, which helps transfer heat away from the CPU die to the IHS faster than normal thermal paste. And the heat spreader job is, obviously, spreading heat. So the heat is no longer focusing only on the CPU die, but is transferred to a larger area, resulting lower temperature. In the second case, although we have direct die cooling, thermal paste transfer heat away from the CPU much slower than indium solder and IHS combo, and this makes the heat stuck on the CPU die. That's why I could have low CPU temperature during idle, but way too hot during load. But wait, hadn't Intel used thermal paste on previous generations? Yeah, compare the 9900K to the 8700K for example. The 9900K is 50% thicker. It also comes with 2 extra cores and 4 extra threads, meaning it produces more heat than the 8700K. So, in conclusion, the 9900K requires metal on the die. I did not have any liquid metal to apply on the CPU die, so I could only use my PC to browse the internet and watch YouTube, while waiting for 3 days for the thermal Grizzly Conductonaut to arrive. For this part, I think you guys are all familiar with the procedure. Push out a tiny ball of liquid metal, drop on the die, then spread. I did not add any liquid metal on the CPU cooler because I think this was enough. After running some tests, I came back, removed the cooler to check. It did make contact with the CPU die. I also added one thin layer on the CPU cooler and redid some tests. There was no difference between before and after. So, applying liquid metal on the CPU die is enough. You do not need to do on both. I also added a little bit of liquid metal on this copper M.2 heatsink in order to see how liquid metal affect copper. So I will let you guys know the result within 1 year in the future. The testing method is doing multiple rendering tests with Cinebench R20. Why did I use Cinebench instead of any stress test application? Firstly, I was doing this because I want to know how hot the CPU can be with rendering, as the most intensive task that I would do is 4K software rendering with Adobe Premiere Pro. Second, I was too excited to delete the chip that I completely forgot about i9-9900k. Anyway, I have tested a CPU before and it was stable with the OK temperature at 4.9 GHz, but 5 GHz is still a mystery. First chart was the result of 4.7 GHz. In the first one, I turned off multi-core enhancement and manually set the voltage to 1.235 volts, which locks all the cores at 4.7 GHz. With direct die cooling and liquid metal, average temperature dropped from 75 to 70 Celsius, while the peak temp dropped from 77 to 72. Then I went to BIOS, set multi-core enhancement and voltage to auto. And here is when things got interesting. During load, all the cores were locked at 4.7 GHz, but the average temperature still jumped to 82 degrees, with the peak temp was at 85. Then I changed the multi-core enhancement from auto to enable. That's when I could see the clock speed reaching 5 GHz boost. I have no idea if this happens to Asus boards only, but if you have one and just want to use the stock settings, make sure to set multi-core enhancement to enabled. As you can see that not only I lost performance but also gained extra heat. Anyway, with liquid metal and direct die cooling, my average temperature was at 80 C and peaked at 86 degrees C. At 4.9 GHz, my system was cooled down by 6 degrees in both average and peak temperatures, from 85 to 79 and 87 to 81 respectively. For 5 GHz I could run with 1.35 volts, but I have to disable my overclock RAM and run with XMP profile instead. For 1 hour of i9-9900 with my fans blasting at 100%, my average temperatures was around 82 degrees with only one core hit 90 degrees while the others stay below 86. I also test with Adobe Premiere Pro and render a 4K 60fps high bitrate video. Average temperature was only around 75 and max temp hit 84 degrees C, but the system now runs much quieter than before at 4.9 GHz. And finally, here's my Cinebench R20 score with the application priority set to real time. Here's some quick Star Wars Jedi Fallen Order gameplay. With everything maxed out at 1080p and the DX Story was used to record the video with lot less quality. The max temperatures was only 72 degrees, while the average was only 65. So, was it worth to do? It really depends, but for my case, it totally worth the cost, time and effort. Even though I only could scrap off around 5 to 6 degrees. It may sound small, but for me it's the difference between a loud and quiet system. For higher clock speeds such as at 5 GHz, those small degrees can also mean throttle or not. Again, if you don't really care about the CPU warranty, I think $50 for a full deleting kit and $15 for the liquid metal is a nice and fun experience to do.
It'll be good for us. Here he is, Chief.
An error has been detected on line 10A. All our clamps are jammed. I need 2 workers to climb up and secure the cables.
That's not an easy maneuver.
The guild will double your pay for this shift.
Come on, Cal. What's our score? That couldn't hurt. Huh?
Okay.
All right, let's go.
And that's it for today's video. I hope you enjoy it, and I'll see you all in the next one. Bye bye.
Sorry, Cal.
Don't worry about it.